Are you all there? Can you hear me? Okay, good. Everybody's back. All right, so I want to go back and I want to look at the case now when gamma is 5. Okay, I want to look at the case when gamma is 5. What does this mean? If gamma is 5, then according to the person in the garage, the truck is 6 meters long. So to the garage observer, the truck is just as long as the garage, which means then that when the back end of the truck hits the front end of the garage, the front end of the truck will hit the back end of the garage at the same time. Those two events will be simultaneous. So according to the person in the garage, they're going to see the two events happen at the same time. When this part of the truck hits the rear end of the garage and when the back end of the truck hits the front end of the garage, or reaches the front end of the garage, they're going to happen at the same time. But the person on the truck is not going to see that, because the person on the truck is going to see a garage that's shorter than 6 meters by a factor of 5, because gamma is 5. Now I want to go back to the equation on the previous slide, 2 slides ago, where I calculated the time when the front of the truck hits the rear end of the garage. Okay, and I got minus 98 seconds, nanoseconds, sorry. And I have this equation here. Now, when gamma is 5, this is going to be 5. However, this time is not going to be 5. This time is going to be 0 because, according to the person in the garage, both events happen at the same time. And then this value then becomes minus 97.9 nanoseconds. 97.98 nanoseconds. Okay? So to the garage observer, oops, I have a mistake here. To the garage observer, the truck is 6 meters, not 1.2. To the driver, the garage is 1.2 meters. What happens if the truck stops in the garage? Of course, the truck would have to stop instantaneously, but what happens if the truck stops in the garage? The truck then is not going to be an inertial reference frame. And according to the observer, the truck will fit, the observer in the garage, the truck will fit in the garage. The truck is going to end up being, and in the end, the truck is going to end up being in the reference frame of the person in the garage. At some point in time, they're going to be, the front end and the back end of the truck are going to be in the garage. What if the back door of the truck, the garage, was replaced with an infinitely thick wall? The truck, according to the truck, is going to slam into the back door. Okay. And the truck would have to somehow collapse. Now it turns out that when the front end of the truck hits the concrete wall, there's a wave that's going to be sent along the truck. It's not going to be sent instantaneous. Right, there's going to be a wave sent to transmit the information that the front end of the truck was ran into a wall. It takes time, a distance of L over C. And so what's going to happen is the front end of the truck will start collapsing, but the back end won't. The back end will actually be in an inertial reference frame until the wave hits the back end. So when a truck collides, the front end will compress while the back end keeps moving forward. And in the end, both observers will agree that the truck fits in the garage. There's actually a wiki on this online. You can read about it. I mean, the calculation is complex, but I'm just giving you what the conceptual overview of what this would mean. Okay, so it's an interesting problem. This is, again, related to the pole in the barn paradox. Okay. So I've given you a couple of examples. of the application of the Lorentz transformation, and you're going to see a few more in the homework. Now what I want to do is I want to discuss energy and momentum. While I would have loved to talk about how the concept of momentum changes in relativity, I think I just have to state it because of time. The notes, I have a lot of information about where it comes from, but I think I'm going to ignore it because of time. And I'm just going to state some things and have you believe them. And if you want to know more about, why momentum has to change, the equation for momentum has to change, you can read about it elsewhere. Our book doesn't even derive the equation for momentum in the relativistic case. The relativistic corrections to V causes momentum conservation to become dependent on the reference frame. The Lorentz transformations work no problem. They have no problem when you apply the Lorentz transformations to E and M, electricity and magnetism, to the subject of this course. But there are problems in applying the Lorentz transformations to concepts of mechanics. And as a result, the concepts of mechanics kind of have to be rewritten. And so momentum has to be rewritten in a way so that it's consistent with Einstein's first postulate that all the laws of physics are the same in all reference frames. So I had a bunch of slides that I was going to talk about regarding, I had a development talking about where the equation comes from, but I'm going to skip it just in the interest of time. So I'm going to just go to the results. Okay. It turns out that because of relativity, momentum has to be redefined. Momentum is not just m times v anymore. And in fact, even this definition, of momentum is really not sufficient. For, if you want to apply it in all fields of physics. And you would see this in advanced levels, but I'm just saying that. Okay. So, in order for the concept of momentum to be consistent with the Lorentz transformation, is also the idea of force, because dp dt is force, we have to write momentum in the following way. And this is how we define momentum. P is equal to gamma times the mass times u. U is the velocity of the object with respect to the reference frame you're in. Okay, for now we're in our frame, which is not moving. We're moving with the event, so. I'm sorry, let me rephrase that. We're in a stationary frame, okay? Gamma is a little bit different, okay? This gamma, and I should really write a subscript, is the gamma associated with how fast the object is moving. And so we write it like this. So this gamma now is associated with just with how fast the object moving. There's still another gamma associated with the motion of the reference frame. And we probably won't need the other gamma here unless we change reference frames. Okay. So this gamma has a different meaning. Okay. This gamma has to do with the speed of the particle. The gamma we've talked about previously has to do with the motion of the reference frame. So we need to distinguish between those two. Now when we write this form of the momentum, momentum is conserved in all reference frames, in all inertial frames. Of course, when u over c is small, then this thing is 1. So in the limit, as u over c is small, then we get the classical definition of momentum. So it agrees with it. But now m is really a function of velocity. This term really represents the mass. And so it reflects the fact that mass is changing. And we'll see that when we talk about the energy equation. Now, if you take the work energy theorem, and again, I'm not going to, because of time considerations, I'm not going to go through derivations, even though I have all the derivations in your notes. If you take the work energy theorem, remember this, right? And you apply it for the relativistic case, oops. you can show that the work done is equal to, I'm just going to state the equation, gamma sub u mc squared minus mc squared. Okay? This is the kinetic energy. So the work that you do on an object changes the kinetic energy given by this equation. Now, this term is called a rest energy. Okay. The work done on the particle raises the rest energy of the particle to this value. What is this? This is the mass times speed of light. This is the mass times gamma times the speed of light. This is the total energy it has. It's going to be the kinetic energy plus the rest energy. So kinetic energy is not equal to 1/2 mv squared in relativity. Kinetic energy is equal to this in relativity. Okay. This is the new mass of the system. The mass has changed. This means that if you energy is added to the system, the mass will change. Regardless of how you add the energy, the mass will change.
Does that also work if you take energy away?
The mass will decrease.
Okay.
So here's an example. If you take two nuclei, like a proton and a neutron, and you add their masses, you get a certain value, right? These two are separated. They have a certain mass. So let's say this is a proton and a neutron. Now you combine them into one big object. You do some sort of experiment where you can combine them in one big object. Okay? This mass is lower than this mass. The rest energy has decreased. Why? Because of the fact that the potential energy, in order to get the systems to combine with each other, the potential energy of the system actually decreases. The change in potential energy is negative. Just like when you talk about the sun going, the Earth going around the sun, right? Potential energy is negative. Okay. So what happens is the energy is stored as potential energy, and so the mass decreases. If they repel, then the mass will increase, and that's going to result in kinetic energy, because they're going to fly apart. Does that make sense? This is the famous equation, E equals mc squared. It comes from this, and I didn't go through a derivation, it's in your notes, but taking the integral of f dot dr and rewriting it will give you this expression. This represents the fact that the mass of the object has changed when you've done work on it, regardless of how you did it. Okay? So now we're looking at energy in a different way. Questions on this? Let's look at the equation for kinetic energy. Let's look at this equation. We can write the equation for kinetic energy, and I'll come over here. As K equals gamma mc squared minus mc squared What if U is small? In other words, what if this term is small? Not zero, but small. Well, you folks have all had Calc 2, right? I think. And in Calc 2, you learn that you can expand this thing when this term is less than 1. If U over C much, much less than 1, we can write as this is approximately equal to do you remember doing these expansions? I hope. In Calc 2.
Is that a 1 prime?
I'm sorry?
The 1 prime minus U squared over C squared?
Oh, no, it's just, sorry. 1 minus U squared over C. It's basically, I rewrote this.
Yeah.
So I did an expansion, right?
Yeah.
Okay. So I'm going to just keep these first two terms. This term and this term disappear. And then I get, oh, this C cancels with this C. And I get 1/2 m u squared. 1/2 mass times velocity squared. So when U is small, then basically we get our old equation for kinetic energy that you learned in Physics 205. So even the equation for kinetic energy has changed. It's this. But in the limit as U over C approaches 0, it does approach 1/2 mv squared, which is nice. So it shows basically classical mechanics, in the limit of slow speed, relativistic mechanics merges into classical mechanics. Okay. Now, what happens as U approaches the velocity of light? What happens when U approaches the velocity of light? Well, gamma approaches infinity. This term approaches infinity. All right? And so it says that the total energy is infinite. That would mean then that would require an infinite amount of work to get the speed of the object to the speed of light. But basically, it's telling you the speed of light is a limiting speed, because to get to that point, you need to put in an infinite amount of energy. Now, the conversion of rest energy into kinetic energy with the corresponding loss of, let's say, rest mass, that happens in fission process. I shouldn't really say loss of rest mass, but change in rest mass. Occurs in radioactive decay processes, nuclear fission processes, nuclear fusion processes. And so this equation is used in those cases where that effect is big, and it's a lot of energy. We don't see it with macroscopic objects because it takes an enormous amount of energy to convert the mass of an object into all energy. Okay. Now, I want to write down another equation for you for total energy. There's a couple of ways to write total energies. If you take the equation for momentum, that I showed you and solve for U squared over C squared, you can rewrite the total energy in a different way. So we can write the total energy as gamma mc squared, where this is the new mass, this is the mass of the object. This is the kinetic energy plus the rest mass, or you can write it in the following way. Okay, E equals the momentum times the speed of light squared plus the rest mass squared, the rest energy squared. In order to get this, you have to take this equation and then solve for U squared over C squared. Okay? And then plug it into here. It's actually a lot of work, so I'm not going to do it. Just believe me. Now, it turns out that if you take this and you get this by squaring both sides and putting the PC on the other, p squared c squared on the other side. This is the same in every reference frame. This quantity, no matter what reference frame you're in, is the same value. This represents the length of a vector that has 4 components in relativity. And it has the same value in all reference frames. It's almost like it's analogous to the distance between 2 points in math. This has the same value in all reference frames. It's the rest energy. Okay? One more thing. Does light have energy? Does light transmit energy? What does the term P represent? Momentum. Right, just like in physics 205, Tristan. P is momentum. All right, this is our new definition of momentum. So does light transmit energy? And granted, we haven't done any E&M in this course, but what do you think? It does, right? Light does. I mean, we kind of experience the idea that light transmits energy. Right? If you have solar panels, you know that light transmits energy, right? And we'll find that, we'll learn that light consists of particles that have no mass, and you learn in 215. Light consists of particles called photons. What's the mass of a photon? Anybody want to guess what the mass of a photon is? It's 0. Okay, so light can be thought of as a massless particle. So the energy of a photon, or energy of light, basically can be written as its momentum times c. If light carries energy, it carries momentum. When we get to chapter 34 at the end of the semester, we will have an equation that is very similar to this. Okay? So massless particle, their energy is just P times C. So these equations, along with conservation of momentum, will allow you to do a lot of problems. So let's consider a simple problem that you learn in mechanics. You did this in physics 205. I know you did. Okay. Is illustrative of the concepts that we're talking about here. So suppose you have 2 particles of equal mass. They come towards each other with speed u. Same mass. They collide and stick together. What happens?
They're treated as one particle afterwards.
Yeah, so afterwards you just
mass.
have one. You're right. So basically you have this, and this, which we can also write like this too, right? Either way, it doesn't matter. And it turns out if we treat it as two particles like this, or like in this problem, it's not going to matter. And really what I should have done is treat it as just one big particle. And to be honest, I did steal this from a book, and now that I realize I don't like the way they do it, I'm gonna follow the way they do it. They're gonna treat it as just two big particles that are stuck together. And they're not gonna move, right? They can't move afterwards because why?
Is it elastic or perfectly inelastic?
Yeah, but I mean,
so that they don't bounce.
I'm sorry?
Well, they don't bounce off each other anyway.
Yeah, so, but they have equal and opposite what? Before the collision. Yeah, but more important than speed. Momentum. They have equal and opposite momentum before the collision. So the total momentum of the system is what? Zero. And whether you write a momentum classically or relativistically, the total initial momentum is still zero. And if momentum is conserved, then the total final momentum is zero. And if they stick together, you know that they're not going to be moving afterwards. Right, by conservation of momentum. There's just one big object just sitting there. What's conserved here? Momentum is conserved. What about energy?
Doesn't all the energy become potential?
Yeah, or thermal energy, right? However, it could be thermal energy or thermal energy, however you want to describe it. However, they stick together, right?
Yeah.
But in physics 205, did you conserve energy, kinetic energy, in a collision? In an inelastic collision, I'm sorry. When you did conservation momentum problems in physics 205, did you conserve kinetic energy in those problems? The answer is no, right? You only use conservation momentum to solve completely inelastic collision problems because kinetic energy was not conserved. But total energy is. And the way we write energy in relativity takes into account total energy. And any changes could mean that the kinetic energy is converted into thermal energy. So if the mass changes, that means some energy gets converted into some other form of energy. So, what's my total initial energy of the system? I have each particle moving with speed mu, one going to the right and one going to the left. One particle has total energy equal gamma m initial c squared. Each particle has this energy. The total energy then is going to be the sum of these two. and energy is conserved after the collision. So, and I'm going to put gamma sub u here. What's gamma after the collision?
Was it just normal gamma? Someone in the comments said 1.
Yeah, it's 1, right? Because this is 0. By the way, I can either write this as a 2 or just as just a big M, but I'm going to look at the mass of each blob, I guess. So what's the final mass? So the mass of the system has changed. The mass of each particle has increased. And that's because the kinetic energy of the particles has been converted into thermal energy. What I want to do is calculate, I want to calculate the change in energy of the system. Okay? I want to calculate the change in energy of the system. I want to get delta E. Delta E is going to be my final energy minus my initial energy. Okay? Actually, I'm going to look at the change in rest energy. Sorry. So this is the new rest energy. This is gamma initial. What does this come out to be? It's going to be that's my change in energy. Now, what if U is small? Then this term we showed before can be approximated as the following. Make sure I have the right sign. And it gives me mu squared. At low speeds, this is the change in energy. Okay. It's the change in rest energy at low speeds. What is that equal to? Well, classically, how much energy does this have? From a classical point of view, what's the kinetic energy of this particle? Isn't it just 1/2 mu squared? And isn't classically, isn't this the kinetic energy 1/2 mu squared? What's 1/2 mu squared plus 1/2 mu squared?
mu squared.
Mu squared. So the initial kinetic energy classically was mu squared, then it's gone. Where did it go? Into increasing the mass of the system. That clearly shows you that. Okay. Questions on this? As you do these problems involving conservation of energy and momentum, you will find, to me, they're a little bit easier than the problems we did at the beginning of this discussion. Okay. So I want to look at the collision of the particles from the frame of the object moving to the right. Okay. I want to look at this from a different reference frame, from the frame of the particle moving to the right. Which means then that I have to do a Lorentz transformation on the particle. Okay, so let's do that. Let me erase the board. So now same collision, oops, wrong towel. Same collision, I gotta find my eraser. But from a different reference frame. Okay, so I want to know, so I'm going to be in this frame, I'm going to be sitting on here, and I'm going to be watching this guy. How am I going to write this? So what I got to do is say, I'm sitting here, I'm stationary, and what does that mean though? How do I deal with this? How do I do this? If I'm sitting on top of this particle, I want to find U prime. U prime Let me double check and make sure I have everything written down right. What's V in this case? What's V in this case? So I'm sitting on this particle, and this thing is coming towards me. Look, if I use a reference frame of the particle that's moving to the right, isn't the Earth's reference frame moving to the left? I'll write it down. Isn't that true?
Why would Earth be moving at all?
Well, let's say
Or is it just rotating?
here's an object, right? And I move that way. I'm driving in a car to the right. If I'm looking at that object, doesn't that object look like it's moving to the left to me?
Because it's getting closer?
No. Here's an object, right?
Okay.
Okay, here's a piece of paper. I drive to the right.
Okay.
Isn't this distance between me and the paper increasing to the left?
Yes.
That means then that piece of paper is moving to my away from me, right?
Yeah.
Okay, so from the reference frame
okay.
of the person in the car, right? I'm talking about the reference frame of this person. So if I'm looking at a tree, the tree is moving to the left.
As you're moving to the right, right?
Correct. Yeah.
Okay. All right.
Okay. Then what? I mean, aren't both of these going to add together? I mean, the reference frame is moving to the left with speed u. This particle is moving with speed u. So then shouldn't u sub x prime have a 2u? I mean, think about this from classical mechanics. I'm driving to the right at 60 miles per hour. And a car is driving towards me at 40 miles per hour. How fast is that car moving towards me? I'm driving to the right at 60 miles per hour, and a car's driving towards me from the left at 40 miles per hour. How fast is that car approaching me? Isn't that 100? Yeah, it's 2u, right? It's 2u because each one of them are moving with speed u. And I'm using the same idea. It's going to be 60 plus 40 is 100. So in this collision, I'm stationary. This guy's moving with this speed towards me. Oops. Okay, so this is the picture now from that reference frame. So what's my total initial energy? Well, this guy's stationary. What's my total initial energy for this guy? This one's gonna be a mess because now in my frame, what's going to happen? If the objects come to rest in the Earth's frame, that means, and the Earth is moving, in my frame, the Earth is moving to the left with speed u, then my final energy is going to be this. If you solve for gamma final, you get the same answer. You have to. Okay? If you solve for gamma final, you will get the same answer as we did when we solved it from the Earth's frame. If you solve for M final, I get M final equals gamma M initial. Okay? But I'm going to leave the algebra up to you because it takes a while. You can also then show that momentum is conserved. You can use conservation of momentum because if I'm standing there on the object, I'm not moving. This guy is moving. And so the initial momentum of the system is just the momentum of the object coming towards me, which is going to be a mess. okay, times this thing again. I've written it in compact form in the notes. And this has got to be equal to the momentum of the final system, which is 2 gamma m final u. And you will find, if you do the algebra, that m final ends up being gamma m initial as before. And this shows that conservation of energy is the same, is consistent in both reference frame. If the rest mass does not change, energy and momentum won't be conserved. Go ahead and try to calculate the rest energies, the change in rest energy for low velocity in this particular case. You'll get the same thing. Okay. So I'm going to skip the next example for now. I want to talk about one more thing. This information, this table, gives you the mass of various particles. Photons, electrons, positrons, protons. By the way, a positron is an electron with the opposite charge. These are particles that are part of the atom. These are atomic particles. And they've listed the rest energy. And I can calculate the rest mass. So, for example, proton has rest energy of 938.3 MeV. Now, what the heck does that mean? So let me explain what that means. Let me explain what the last column in the table means. It means that the mass of the proton times the speed of light is equal to this value. What's an MeV? Well, first of all, what's the mass of a proton? We know its mass indirectly. We don't have scales small enough to weigh them, okay? If I take this mass and I multiply by the speed of light squared, I get the rest energy. And this will be in joules. So this whole thing is in joules. But this number is going to be small in joules. Okay? So when we deal with small particles, we have a unit called an electron volt. And it's equal to 1.6 times 10 to the minus 19 joules. And we're going to see this later on in the course. I'm introducing it to you now. So if I take this value and divide by 1.6 times 10 to the minus 19 joules per electron volt, I'm going to get an answer in electron volts. Now, 1 million EV is equal to 1 MeV. And so this ends up being 938.3 MeV. That's where that comes from. Okay? We're not going to use joules. It's cumbersome. We're going to use either electron volts or mega electron volts. Now, how do we express mass then? Do I want to write it this way? I can, but people who are in high energy physics, they don't write the mass of the proton this way. They do the following. They divide both sides by c squared, and they say that the mass of the proton is 938.3 MeV over c squared. So people who do relativity problem involving small particles, they express the mass of these tiny particles, not in kilograms, but in terms of MeV over c squared. So all I got to do is multiply times c squared. I know the rest energy. I don't have to do any cumbersome calculation. That makes sense? It's very unusual. You've probably never seen this before. And so the electron is 0.511 MeV. Its mass then is 0.511 MeV over c squared. So I could write the mass of the electron like that. Okay. The mass of the neutron, I will write it this way because it's based on the rest energy. Just another unit to express mass. Instead of writing, it's like 1.67 times 10 to the minus 27, I write it this way. And the reason why is because when I'm doing relativity, if I want to find the rest energy, I multiply both sides by c squared. The c squares cancel. I have the energy I need. Now, if you look at the last item on the table, in that table, the last item is the deuteron. The deuteron is a proton and a neutron stuck together. Okay. If you look at that table, you can do the calculation very quickly. If you take the rest energies of the proton and the neutron and add them together, they will be less than the mass of the deuteron. That difference in mass, that loss of mass, goes into binding the two together. Just like how the Earth is basically bound to the sun and it circles around the sun. Same idea. So the energy difference is how much energy is required to separate the proton and the neutron. If you add that energy, you'll blow apart the deuteron. And you'll have the two particles. of those masses. Okay, so if you take 938.3 plus 939.6 and you compare it to 1875.6, you will see you get different values. The difference is the binding energy, how much energy it takes to take that thing apart. Okay, so let's do that. Let's do the calculation. Okay. The rest energy of the proton is 938. These are very simple problems. The rest energy, because you'll have problems like this in the homework, 939.6. Okay. This comes out to be 1877.8 MeV. The rest energy of the deuteron, you're going to be given it to you, okay? You have to look it up. You're not going to remember this. The difference is 2.2 MeV. That lower mass of the composite system, when they're bound together, is due to the fact that it takes energy to bind them together. It takes 2.2 MeV to bind them together. If you want to convert it to joules, go have at it. It's going to be about 3.5 times 10 to the minus 19 joules, which is a small number, which doesn't mean much when you're used to doing numbers that are like hundreds of joules in classical mechanics. We do a lot of interesting problems. I mean, they're pretty straightforward. Let me do one more. In a typical fusion reaction, a tritium nucleus and a deuterium nucleus fuse together to form helium plus a neutron. How much energy is released? And you're going to have problems like this, and these are actually pretty easy. That's why I'm saying this. The material here is a little bit easier once you get used to working with the equations. So let me talk about what that phrase means. A tritium nucleus is basically the nucleus of a hydrogen atom with 2 extra neutrons. This is the mass. The neutron and the proton are about the same mass. So there's 3 masses that are about the same. Okay? And so you have 3. A proton, a neutron, and another neutron bound together to form this thing. And this is how many protons there are in there. You blast it into a deuteron, which is a proton and a neutron. I mean, very high energy. And you form a helium nucleus, which has 2 protons and 2 neutrons, and it has 2 protons are written here. the total mass of the 2 protons and 2 neutrons are put here, plus a neutron. This has no protons, but one particle is about the same mass of the proton. If you compare the mass, the rest mass here and the rest mass here, or the rest energy here and the rest energy here, you're going to have different values. In this particular case, energy will be released. So let's do some calculations. Okay. The rest mass, or the rest energy of this guy, again, you have to look it up. And you need all the digits. And the rest energy of this one, rest mass of this one, the rest mass would be divided by c squared. Okay. This one is 1875.6. And this one is if you add these two together and these two together, you will find that this is bigger than this. That means that something flies apart. Energy is released. The energy afterwards is greater than the energy before you started from, because energy is released. The mass afterwards is greater than the mass initial beforehand, because again, the energy is released. So let's calculate the release of energy. We're going to take this sum, this is what I have afterwards, and subtract what I put into it. The difference is that this much energy is released per event. Every single time this reaction occurs, this how much energy is released. That's a lot of energy. Because this is per atom. Okay, per collision. So that's a lot of energy. A lot of these problems in relativity involving changes in mass, they're actually, for us, these problems should be pretty straightforward for you. Okay, the ones that are a little bit harder are the ones that involve conservation of energy and momentum. I have created a video of a problem that involves both conservation of energy and momentum. You guys better watch it. Okay? So I have a few more things to talk about in terms of conservation of energy and momentum next week. And I have another example to go over next week before I start the new unit. And if you are uncomfortable with this topic, we're almost done. It's a short unit. Even the exam is worth a few points, a half a regular exam. So, you're going to be, I think you'll be okay. All right. And since the exam is, I'm going to make the exam in person, it's not going to be as, they're going to be more related to, similar to the homework problems you're going to be doing. Okay. Yeah, Tristan, because the exam is in person, my goal is to make, generally make the exam problems standardized, meaning they're going to be something, common type of problems that you would see in a textbook. When I give the exam online, then I don't do that, because You can't Google them. I mean, they're easy. Standard problems are easy to Google, okay? And we've had issues. We've had a lot of problems in our courses. And so I had to make exams that were not standardized. But when you're doing the exam in person, they're going to be pretty much standard problems. Okay, I'm trying to find a collection of problems that are standard. So because this unit I've only done in the online version. In fact, last semester was the first time I did this unit like this. But the exam was online, so the sample you have right now is the sample for the online exam, which is a little bit harder. Okay. I'm going to try to make an example which is a little bit easier for you guys, so you get to see the difference. Typically, when I write an exam, I think I write basic problems and then I write one that's challenging. I always do that. Okay, and I'm known for that. When I give my exams, there's one that's challenging and the other ones, well, I mean, are more standard. I guess they're challenging too, but not as challenging as the one problem. Okay, so that's typically how I write my exams. You can ask other students who've had me when the classes were in person. And we can talk about more about the exam next week. Okay. And then I'll get a gauge as to where you're at next week too. All right. Please come to my office hours on Thursday and ask me your questions. All right. I need to go to a meeting soon. So I will see you hopefully Thursday, if not Thursday, Friday.